we're going to introduce a concept of what is called a planar graph, which is really very unlike earlier stuff we've discussed. So we focused in the previous video on isomorphism of graphs as a way that distinguishes when two graphs are fundamentally identical even if you draw them slightly differently. But now we're actually going to define something that, at least at first glance, does appear to be a property about how you draw a graph or how it appears to you. A graph is called planar if it's possible to draw the graph in the two-dimensional plane in a way that edges do not cross each other. So you can draw edges as crazy as you want. They don't have to be straight lines. However, you're simply not allowed to have two edges cross each other. If it's possible to draw a graph in that way, it's called a planar graph. So for example, here is a planar graph. There it is. Since the graph is actually drawn without edges touching each other, it's definitely a planar graph. It is possible to draw it without the edges crossing. But here is a non-planar graph. Okay, so we've certainly drawn it with some crossing edges. That doesn't actually prove that it's not possible to redraw the edges in a way so that none of them cross. It is true that this is a non-planar graph. We just haven't actually proved it. Okay, no matter how you try to redraw this graph, these 5 vertices with the certain connections that are drawn, it will not be possible to draw it without crossing some edges. In our discussion of planar graphs, we're going to begin with complete graphs. So remember that a complete graph on n vertices, any 2 vertices you pick have an edge between them. So a complete graph on 3 vertices has 3 vertices and all possible edges, just without multi-edges. Well, which of these graphs are planar? The graph k sub n, the complete graph on n vertices, is planar if and only if n is less than or equal to 4. So 0 through 4 vertices, you can draw a version of that complete graph with no edges crossing. 5 or more vertices, and you cannot. Well, we'll do an informal proof. For 0 through 4, we're claiming that these are planar graphs. And to show a graph is planar, all you have to do is draw it in a way that has no edges crossing. And here we go. 0 vertices, I'm sorry, no problem, just don't do anything. 1 vertex, there are no edges to draw, so not a big deal. If I add a second vertex, I just have to draw an edge, and since there were no existing edges, I certainly haven't crossed any. Okay, once I have these 2 vertices down, I can lay down a third vertex and then connect them. And now I can put a 4th vertex in the middle of that triangle and connect out to the corners of the triangle with edges. So up to 4 vertices, it's possible to draw without crossing edges, and therefore they are planar. Now what if I try to add more than 4 vertices, so at least 5? Well, if I can just show it's not possible to draw a 5 vertex complete graph without edges crossing, then as soon as I start adding more vertices past that point, the result will still hold, because if I have a complete graph on 7 vertices, I have 7 vertices and I have all possible edges. So if I pick any 5 of them, I must have all possible edges between those 5. In other words, there will be a 5 vertex complete subgraph. And since we are going to argue that you can't draw a 5 vertex complete graph without edges crossing, since those will appear as subgraphs for any larger number of vertices, it will hold that you can't draw a larger complete graph without edges crossing, since it will contain that 5 vertex complete graph as a subgraph. So as an informal argument as to why k sub 5 can't be drawn, imagine we have k sub 4, and we've drawn it here. The next vertex has to go somewhere. So maybe I put it inside one of these smaller triangles. Well, from this vertex, I can connect out to these 3 vertices, but how am I going to connect up here? And maybe I put the new vertex outside the graph, in which case I can connect here, here, and I can even draw an edge that goes all the way around to connect to this vertex, but I'm not going to be able to reach the one on the inside without fundamentally crossing one of these edges here. And that's not a full proof, but it's a reasonable argument. Well, if we've talked about complete graphs, we can talk about complete bipartite graphs. So a bipartite graph, remember, is one in which we have 2 sets of vertices, and edges can only go between those 2 sets, but not within them. So suppose I have 2 vertex sets, and I have all possible connections from the first set to the second, but I don't have any connections within the 2 vertex sets. That's called a complete bipartite graph. In other words, it has as many edges as possible without violating the bipartite condition. So if I have a complete bipartite graph where the first vertex set has m elements and the second has n, and by convention that second number is larger than or equal to the first, we write it as k sub mn. So for example, k sub 2, 4 is going to have a set with 2 vertices and a set with 4 vertices and all possible connections between them, like this. So on top, we have 2 vertices, on bottom we have 4, but those two sets are connected between each other as much as possible. Well, the theorem about which complete bipartite graphs are planar is as follows. If the smaller number, remember m had to be the smaller of the two numbers, is 1 or 2, then that complete bipartite graph is planar, but as soon as the smaller number is 3 or larger, no. So for m equals 1, a planar presentation is pretty straightforward. For example, you can just imagine this vertex isn't here, so I have 1 vertex and then I have 4. So k1, 4, just stick 1 vertex here and draw all these connections. And if I only have 1 vertex in this top set, it doesn't really matter how many go in this bottom one, just line them all up and draw all possible connections between them. Okay, so for m equals 1, the second number doesn't matter. I can put the 1 vertex on top and draw all possible connections no matter how many vertices there are. Well, what about m equals 2? Instead of drawing this vertex up here, you can imagine drawing it down below. So if I drew this vertex down below, I could have the second vertex down here and just connect them up. So I would have 1 vertex on top connected down to as many as necessary, and another vertex on below connecting up. So for m equals 2, I can draw it without any edges crossing, and therefore it is planar. Now, as soon as m is bigger than or equal to 3, I would have to have at least 3 vertices in each of the two collections, and I would have to have all possible lines between them. So I would have k sub 3, 3 as a subgraph. And k sub 3, 3 is not planar. We're not going to really go over a proof or even draw it out, but I suggest try to draw 3 vertices in one set, 3 vertices in another, and now connect all vertices on top to all vertices on bottom. Well, now this one I can connect around, this one I can go all the way around, and this one I can connect here. Now this vertex on the top connecting to all 3 on the bottom is going to be an issue. I can easily do 1 and 2, but now how am I going to get from this vertex to this one? It will no longer be possible to do it without crossing some edge. And of course, that's not a full proof, okay? That's just based on my one attempt to draw it, but try to get really clever with connecting your top 3 vertices to your bottom 3, and you'll never be able to do it without crossing somehow. So since k sub 3, 3 cannot be drawn without crossing edges, neither can any k sub mn, where the smaller number m is 3 or larger, because that would contain k sub 3, 3 as a subgraph. One of the most remarkable results in mathematics is what's known as Euler's formula. Euler's formula pops up in a whole bunch of different places. So suppose we have a connected planar graph. So I have vertices and edges, and no two edges cross. Okay? It can actually be a simple graph or a multigraph. Maybe you have multiple edges between 2 vertices, but still they're not allowed to cross. So let V be the number of vertices, and E be the number of edges, and F be the number of regions in the plane defined by the edges, including one region that represents everything outside the graph. And a picture will clarify what this means. Then the number of vertices minus the number of edges plus the number of faces is always equal to 2. So we're actually not going to do a proof, but we will demonstrate it. So here is a simple planar multigraph. Okay, no two edges cross, although we are allowed to have multiple edges between 2 vertices. So how many vertices are there? There's 7 vertices. There's also 12 edges. That's just a matter of counting. Now, what about faces? So the regions defined by the edges, we're going to count 7 of them. So there's this region here. Okay, in between these 2 edges, I have a region of the plane. That's 1. Here's another region, 2. Here is a big region, 3. Here's a region, 4. Here's a region, 5. Here is a region, 6. And then all the rest of the plane on the outside makes 7. So regions defined by the edges are just these areas of the plane fully enclosed by edges. One here, one here, one here, 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 and then everything outside is also counted as a region. So for this graph, we have 7 vertices, 12 edges, and 7 regions. And there they are. And indeed, the number of vertices, 7, minus the number of edges, 12, plus the number of faces, 7, is equal to 2. No matter how you draw a simple planar graph, okay, since it's planar, we draw it without edges crossing, so we have well-defined regions in the plane. The number of vertices minus edges plus faces is going to always equal 2. Okay, and this is a version of what's called Euler's formula. We're not proving it, but it does come up in a whole bunch of different areas of mathematics. Well, since we've talked about drawing graphs, maybe we can talk about coloring them. So if we have a graph with vertex set V and edge set E, a coloring of the graph, unfortunately it is not pulling out your markers and coloring them, although I will say that is a way to discuss it. We'll see very shortly. It's actually a function whose domain is the vertex set and the codomain is this set S. The elements of S are called colors, and a proper coloring of a graph has the requirement that if there is an edge connecting 2 vertices, then those 2 vertices have different colors. So you assign colors to vertices, and if 2 vertices are connected by an edge, you're not allowed to give them the same color. So intuitively, we can really think of this in terms of colors. We simply color graphs by putting a color on each vertex without using the same color to connect to adjacent ones. On a formal level, they don't actually have to be, visual colors. You can just label them with numbers or letters or something like that, as long as 2 vertices which are connected are not given the same label. So here's a graph with one legitimate and one illegitimate coloring. So here's the basic graph, okay? We have 5 vertices and some various edges. So what we need to do is assign colors to vertices so that no 2 adjacent vertices have the same color. So this is legitimate. Notice we have red, purple, and green vertices. And while I do have 2 red vertices, they're not connected by an edge. And while I do have 2 purple vertices, they're not connected by an edge. But this would not be legitimate because here we do in fact have these 2 vertices, both purple, connected by an edge. So that's not a proper coloring. Coloring in multigraphs. So we didn't actually specify anything about a direction of edges when we were talking about colors. So coloring a directed graph is the same as if it was undirected. In other words, the flattened graph where you replace directed edges with undirected edges. There's no distinction in the definition. Also, a loop, remember, is an edge that connects a vertex to itself. So since a coloring is not allowed to have both ends of an edge have the same color, we conclude that it's not possible to color any graph with a loop because the start and stop vertex, the 2 sides of the edge, would be the same vertex. And so you can't possibly give the same vertex 2 different colors with an actual function. So if a graph has an edge that connects a vertex to itself, if it has a loop, then there is no way to color that graph. Now, if 2 vertices are given different colors, it doesn't actually matter whether they're connected by 1 edge or by a million. Okay, the edges are still connecting 2 vertices of different color. So not only does the direction of an edge not matter, but whether there's multiple edges connecting the same vertices doesn't matter. So a coloring of a multigraph is equivalent to coloring the simplified graph. Remember, simplifying a graph is where you remove redundant multiple edges. So altogether, if we want to talk about coloring of graphs, directed edges and multiple edges don't matter. So all we have to do is flatten and simplify the graph. In other words, just replace it with an undirected and not multigraph version of the same thing, and then we can talk about coloring, and that will be a similar or equivalent way to discuss the original graph. So typically when we're talking about coloring graphs, we just talk about simple graphs. Undirected simple graphs, because direction and multiple edges won't make a difference. Suppose we have a coloring of a graph. Does it exist? Well, as long as G has no loops, yes. If every vertex has a different color, then it's possible to assign a different color to 2 sides of every edge. By giving every vertex a different color, we can color a graph. So the question is typically not, does a coloring exist? As long as the graph has no loops, a coloring does exist. What we do ask, however, is what is the smallest number of colors I can use? So suppose a graph can be colored with n different colors, but cannot be colored with n-1. As you try to remove colors, you might end up forcing two sides of an edge to have the same color. For example, as long as there's a single edge, it's never possible to color a graph with one color, because you'd have to put that one color on the two sides of the edge. So maybe it's possible to color a graph with 5 colors but not 4, or maybe it's possible to color it with 8 but not 7. Whatever that smallest quantity of numbers, smallest quantity of colors that it's possible to use and still make a proper coloring of the graph, that's called the chromatic number of the graph, the smallest number of colors required to produce a proper coloring. So if there's multiple connected components, and remember, connected components of a graph are like two disconnected pieces of the same graph. Well, if one component has a given chromatic number out on its own, and another component has a chromatic number on its own, the colors of the one graph don't really affect the colors of the other because there are no edges in between them. So the chromatic number of each individual component, if you have a graph with multiple components, you're really just looking for the component with the largest chromatic number, the one that required the most colors. That's going to determine what's happening overall. And similarly, for not discussing directed or multigraphs, typically we only talk about connected graphs because if a graph is disconnected, it has multiple connected components, and then you would just be asking, what's the connected component with the highest chromatic number? So when discussing chromatic number, we tend to only talk about connected simple graphs. Also, if we have a subgraph, okay, so I have a graph and I eliminate some vertices and edges. If I had a proper coloring of the original graph, I still have a proper coloring of the subgraph. I got rid of edges. That removes problems. Okay, so any subgraph can inherit a coloring from the original. But if I have a coloring of the subgraph and I try to go back to the original, since I'm now adding edges back in, I might be forcing connections between vertices of the same color. So you can take a coloring of the parent graph and make it into a coloring of the subgraph, but not necessarily the other way. So since any coloring of the original graph does impose a coloring on the subgraph can't have a larger chromatic number. If the big graph can be colored with 6 colors, so can any subgraph. But if a subgraph can be colored with 3 colors, that doesn't mean the original can. So any subgraph has a chromatic number less than or equal to the chromatic number of the graph that it was taken from. So for example, determine the chromatic number of the graph from a previous slide. Here it is. What's the smallest number of colors required to actually color this thing? So we've already seen a coloring with 3. Okay, we had red, green, and purple, and it was a legitimate coloring. So if it's possible to color this with 3 colors, the chromatic number can't be bigger than 3. But maybe it's possible to color it with 2 colors. However, we have this subgraph. Okay, if you look, we have these triangles in the graph. So here is this triangle as a subgraph of the one we started with. Each vertex is connected to the others, so no 2 vertices can have the same color in this subgraph. So this subgraph definitely requires 3 colors. I can't make these 2 the same color because they're connected, and I can't make these 2 the same color because they're connected, and I can't make these 2 the same color because they're connected. So all 3 of these vertices must be a different color. So in the original graph, we do need 3 colors just to complete this part. So any coloring of the original graph needs at least 3 colors. And we've already seen that it's possible to color it with exactly 3. So since it's possible to color it with 3 and impossible to color it with 2, the chromatic number is 3, the smallest number of colors required to produce a legitimate coloring. This graph has chromatic number 3. Let's take a look at another example. The graph below has chromatic number 4. So pause here and maybe sketch it out. Try to produce a coloring with 4 colors. So it might take you some time. Hopefully you played around with it. Okay, there are a lot of interconnections. 4 colors might take a little bit of effort, but you could do something perhaps similar to this. So here is a coloring with 4 colors. I used orange, green, red, and purple. And if you spend some time looking at this, there's no edge that connects 2 vertices of the same color. So it is possible to color this with 4 colors. There are, of course, other possibilities. This is not the only way to do it. So we didn't actually ask you to prove that you can't color it with 3. But you might pause here and attempt to think as to why it's the case. And the reason why this cannot be colored with 3 colors is very similar to why the graph on the previous one couldn't be colored with 2. The previous graph had a triangle, and a triangle can't be done with only 2 colors. This has a square, but a square can definitely be done with 2 colors. Here, for example, we have a quadrilateral, and I can successfully do this with 2 colors. But there is a subgraph in here that if you simplify everything down by only pulling the appropriate subgraph, you can see that it absolutely requires 4 colors. So play around, try to come up with an explanation why this cannot be done with 3. And since it's possible to do this with 4 colors and not possible to do it with 3, therefore the chromatic number is 4. Let's take a look at complete graphs. A complete graph, every vertex is connected to every other. And that was denoted with k sub n. Well, the chromatic number of a complete graph on n vertices must be exactly n. The proof is actually quite straightforward. It is possible to color a complete graph on n vertices with n colors by giving every vertex its own color. So the chromatic number can't be bigger than n. But since every vertex is connected to every other vertex, it is not possible to use the same color twice. If I gave the same color to 2 vertices, since it's a complete graph, those 2 vertices are definitely connected, and therefore that's not a legitimate coloring. So no 2 vertices can have the same color, and there were n vertices. So I need at least n colors. Therefore, I always need exactly n. So a complete graph on n vertices always has chromatic number n. Perhaps if you played around with it on the previous slide, what you could have found was a complete graph on 4 vertices as a subgraph. That's why the previous slide could not be done with 3 colors. It had a subgraph of k sub 4. So since the previous slide had a subgraph of k sub 4, its chromatic number couldn't have been smaller than 4, and there was a coloring with 4 colors. Well, what about planar graphs? Intuitively, as we add edges, we need more colors. Complete graphs, lots of edges, need as many colors as there are vertices. The fewer edges there are, the fewer potential problems in producing a coloring. But there was another definition about graphs that, in our intuition at least, is related to not having too many edges, and that was, is the graph planar? A planar graph, edges aren't allowed to cross, and that is probably easier if there aren't that many edges. So planar graphs and coloring both seem to depend on, well, there aren't too many edges. So maybe a planar graph, because it doesn't have too many edges, maybe has a small chromatic number. This is a pretty famous theorem. It's called the 4-color theorem. Any planar graph has chromatic number 4 or smaller. In other words, it is always possible to color a planar graph with 4 colors or fewer. The proof was completed first in 1976. It had conjectured a while before that. But the first proof actually relied on a computer program to analyze over 1,834 different cases. So back when we discussed proof by cases, way back when, we did 2 cases and 3 cases, and this was a proof with 1,834 cases. And because there were so many cases, it was not feasible to work them all out by hand. And the computer program was written to complete the proof. Now, the number of cases has been refined. It's no longer a proof by 1,834 cases, but all the proofs that have been done do rely on a computer to assist in analyzing the large number of cases. And the fact that no single person can reasonably be expected to go through and check every single line of the proof was at first extremely controversial. If no person had actually checked it, could you trust a computer? Was it considered proven, or was it just something a computer put on a screen, but we couldn't really count it as a done problem yet? These are what are called computer-assisted proofs. Now, 1976, it was a controversy. It's become a lot more accepted. In fact, there's a whole branch of mathematics and computer science devoted to this called automated theorem proving. And in recent years, there's actually a large open source platform where anyone can contribute and analyze the source code of the theorem proving software, which really helps to open up its acceptance.